Hello everyone and welcome back to my channel. I'm your host Trey, and today we're going to talk about the arithmetic operations. It's a continuation of the previous video on the binary system, and in this video we are going to talk about the actual implementation of the arithmetic operations of binary numbers. Meaning we're going to talk about binary addition, binary subtraction, binary multiplication, and also binary division. Let's get into it. So in our previous video, we talked about um, sign and magnitude. We talked about one's complement. We also talked about two's complement, right? But in this video, we're going to talk about binary addition and subtraction, restoring and non-restoring algorithms, and booth algorithm as general. So without further ado, let's get into it. So binary addition and subtraction has got basic units of basically we're adding binary numbers and we're subtracting binary numbers. So let's get a visual representation of what we mean. So we have two values here. Let's just say we find the value of 5 plus 2 and also find the value of 5 minus 2. Please, for these videos, I know it's easy to lose track of what's happening, so please pay attention and try to follow up with what I'm actually doing. I'll try my best to explain step by step on how to do these exact processes. So please be attentive, and I'll hope you understand what these are. So let's just say we have the value of 5 plus 2, right? If you know how to write your binary numbers, you know how to represent 5 in binary, and you also know how to represent 2 in binary, right? Good. So now our 5 representation in binary using 4 bits, we have 0, 1, 0, 1, right? And we have 2, which is 0, 0, 1, 0. So for you to add these values, we say that we get 1 plus 0 is 1, 0 plus 1 is 1, 1 plus 0 is 1, and we have 0 plus 0, which is equal to 0, right? And if you notice properly here, we know that the value 1, 1, 1, if you look at your sign magnitude, if you remember sign and magnitude, here we have 4, we have 2, we have 1. So 4 plus 2 plus 1 is equal to 7, exactly. So we have our 7 value there, right? I hope that's just a simple representation of everything. So let's try finding 12 plus 4. So now notice that we have a carry section here, and that will be very important later on. But right now, try to follow me as I go about it. So here we have 0 plus 0 is equal to 0. 0 plus 0 is also equal to 0. 1 plus 1, right, is equal to 2. But the binary representation of 2 is 1, 0. So we get 0 and then we carry 1, like that, right? Good. So 1 plus 1 is equal to 2. The binary representation of 2 is equal to 1, 0. So we get 0 and then we carry 1. So this one is going to be used to add to this value here. So we say 1 plus 1 is equal to 0. 0 carry 1, right? Or you could say 1 plus 0 is equal to 1. 1 plus 1 is equal to 0, carry the 1, like so. And we have carried that value. So our value here is 12 plus 4, which is equal to 16. And the value 16, using 4 bits, can be represented by 0, 0, 0, 0, right? With carry bits of 1 and 1, like so. If you do not understand, let me go through this again. So now, let's just get rid of that guy. Let me go through this again. Good. So we have 0 plus 0 is equal to 0, like that, right? 0 plus 0 is equal to 0. 1 plus 1 is equal to 2. 2 represented in binary is 1, 0, right? We have a 2 here. 1, 0, right? That's 2 in binary. So we get the 2, we carry the 1 here, like so. We carry it, right? Good. And then we go to our next value here. 1 plus 0 is 1. 1 plus 1 is 0. 1 plus 1 is 2, right? Good. So we get the 0 and we carry the 1. So we have 1 as our carry bit, like so. So I hope you understand how carry bits work and how binary addition works. So now let's go to binary subtraction. Okay, good. So let's find the value of 5 minus 2, right? Good. So last video we talked about 2's complement representation. So now here we have our value 5 minus 2. So 5 is positive. So if it's positive here, our sign bit is going to be 0, right? And we have 1, 0, 1. Great. So now to change the negative to 2's complement. So we change the negative to 2's complement because we are trying to subtract here, right? So we're going to get this value and we are going to change it to 2's complement so that our addition becomes easy. So we're basically transforming subtraction to addition, right? Using 2's complement. So we get the value of 2 and get it to 2's complement. So we have that guy there. So negative 2 here has got a sign negative there, meaning it's got 1, 0, 1, 0. So this is the representation in sign and magnitude of negative 2 using 8 bits. Sorry, using 4 bits, right? So we have negative 2. Changing this value to 2's complement, we have our 1, which is our negative, which is our sign bit there. And then we have our 0, 1, 0. So if we're changing this guy here, so we're going to get the inverse. So this is going to be 1, 0, 1, right? 1, 0, 1 plus 1. 1, 0, 1 is 5, right? 5 plus 1 is equal to that guy there. So now, if we change that here, we have negative 2. We get the sign and our magnitude like so. So we're getting this value here and we're implementing it for adding plus 1. So now we have this guy, we're adding plus 1 there. This is our sign and magnitude. This is 2's complement. So if this is 2's complement here, we're going to get our value there 1, 1, 0, 1. Because we've already changed this guy, right? We've changed this value here, we've inverted it, and then we're adding the 1 value. So this is 1 here, this is supposed to be there. Our 0 that's there is the inverse of that guy, and then our 1 is the inverse of that guy there. And then we're adding plus 1. So now we go back to our binary addition. So we say 1 plus 1 is equal to 0, carry 1, right? Good. 0 plus 1, 0 plus 1 here, this one comes here. 0 plus 1 is equal to 1, right? Good. No carry bits there. 1 plus 0 is equal to 1, and then 1 plus 1 is equal to, this one is a sign, so we don't do anything with it. So what we are interested in is this guy here, right? So now that we have our value here, this is negative 2 in 2's complement. So we place that like so. Not forgetting the sign bit, because this is what tells us that this is negative. So this is negative 2 in 2's complement. So we put it like so, and then now we do our binary addition. Great. So now we turn any negative number, we turn it into 2's complement to make our value easy for addition, right? So when we are subtracting binary values, we turn that binary value into 2's complement so that now we turn it from negative or from subtraction to addition, right? And this is the visual representation of what I mean. So we have 1 plus 0 of 2's complement. Here we're going to have 1. 0 plus 1 is equal to 1, and then 1 plus 1 is equal to 0, right? With a carry bit of 1. Great. So we have 0 plus 1 there, which is equal to 1 plus 0, which is equal to 1 plus 1, which is equal to 0, the carry bit of 1, like so. So meaning our value here is going to be 5, 5 and that there. So when we go back to our original value, we see 5 minus 2 is equal to 3, right? This value in binary, what is 0, 0, 1, 1? Notice that this is positive. So now 5 minus 2 is positive 3. In binary notation, if we go to here, our 4 bits here, we have 1010, right? Good. And then we have this guy. So if we are to place 1 1 here, we have 1 1. 2 plus 1 is equal to 3. Therefore, 5 minus 2 is equal to 3. That's how you find your negative values, or that's how you do binary subtraction. Again, I know these videos are a little bit tricky, so if you do not understand, please watch this video again, starting from the beginning or starting from where you need to understand the concept, and then revisit everything step by step. And if you're having trouble, try writing down what I'm explaining with the visual representations there, and maybe you won't be able to understand what I'm actually saying. If you do understand, congratulations. Let's go to the next step. So now we're done with binary addition and subtraction. Let's go into restoring and non-restoring division. Basically, we're dividing, right? So with all this, we have this type of algorithm for restoring division, right? We have start there. We got A, which is our accumulator, where we're going to store our values. M is the divisor, Q is the dividend, and count is the number of bits that we're going to use. So once we have this, we're going to shift left by 1, the accumulator and the dividend, sorry, and then we are going to say our accumulator is going to equal to A minus M. So whatever value we get from A minus M is going to be our new value of the accumulator. Then we find out if A is greater or less than 0. So if it is greater than 0, so if A is greater than 0, we say our first bit of, or our least significant bit of Q is going to equal to 0, and then we do the addition operation here, and then we count plus 1 and everything. So it's an algorithm. You might not understand it, so let me give you a visual representation of it. Great. So count is equal to n, and count is equal to n, and this is the number of bits of the dividend, right? So the rules are simple. Step 1, shift left the accumulator, right? Once you've shifted left the accumulator, subtract A from M. Great. So subtract A from M, like so. So let's go through it step by step, yeah? So we shift left the accumulator. So we've done step 1. So we've shifted left by 1 value. So you see that here we have 1 1. So you see here that we have 1 1 1, but then we've shifted left. So if we shift left both this one and this one comes here over there like so, and then we have 0 0 like that there. And I've placed this column here to help you understand what's happening in the accumulator. This column normally is not there when it comes to answering this type of question, but I've put it there so that you understand what's happening in the accumulator, right? So that it's easy for you to understand what's happening. So we've shifted left. This is our operation, this is our count. Notice that our count here, if we're using 3 bits for the divisor or for the dividend, then if we're using 3 bits for the dividend, then our count is going to be 3 like so. So now we have shifted left by 1. So now our next operation is to subtract A from M. So then you're going to get this, and we're going to subtract, like so. And now we say that this value here, right, is 3. So now if we're subtracting, this is going to be 1 minus 3, right? And if it's 1 minus 3, then this guy is equal to our value like so. And then when you subtract this, you get your value of negative 2. And naturally speaking, 1 minus 3 is negative 2. So our value is 1 1 0, and this is negative. So now, our most significant bit of A, right, after subtracting, if our most significant bit of A is equal to 0, right, meaning if it's positive, update A, and the last significant bit of Q, meaning this guy, equal to 1. And then we decrement the count value. Else, if our most significant bit is 1, meaning it's negative. Restore A, meaning restore it to its previous shift value. And then our last significant bit of Q is going to be equal to 0. So now we're restoring because our value is 1. So if we restore, then we decrement the value by 1. I forgot to add the decrement. So we decrement the value by 1, and then we have this guy. So M doesn't change. Our divisor doesn't change. It remains the same, right? But then now our rules say that if our most significant bit of A is negative, then our last significant bit of Q is going to be equal to 0. And then we restore the value, the previous value of the shift to this guy. So our value here, we've restored A to our shift value, right? And then now we repeat the process of shifting left. So we shift left now the new value of the accumulator. So now this is going to be 1, 0. And then this 1 comes there. And then now this becomes 3, right? And then we go again of subtracting this one and that one. We have that. So when we subtract 3 minus 3, we're going to get a value of 0. And now 3 minus 3 is 0, and the 3-bit representation of 0 is 0, 0, 0. And we see that our most significant bit of our accumulator here is positive, which is 0. So if, which is positive there. So we go to our algorithm here and say, if A, the most significant bit, is 0, meaning it's positive, we update A, right? So meaning we update A to this new value, and then Q, the last significant bit or the least significant bit, we place it as 1. So in here we put 1 here rather than 0, right? And then we decrement the count as done so. So when we do that, we update A to this new value, and our accumulator value becomes 0, right? And then our dividend value becomes 1, 0, 1. And remember, our divisor does not change, but our count is the one that changes. So now, once we do that, we shift left again. And once we've shifted left, what's going to happen is we're going to have a value of 1, because this one becomes, this one shifts to there, and then this value shifts like so. And then we don't know what this value is here, so we have to perform a subtraction. So when we subtract from the dividend here, we have 1 minus 3. And notice that 1 minus 3 is the same as this guy here, so we know that our value is negative 2. And negative 2 is going to be that, and our first bit of our accumulator is negative, right? It's 1. Meaning we're going to restore the value of A, and our last significant bit of Q is going to be 0. So here we're going to put 0, and we're going to restore A to this previous shift value. That is there. So now, if that's the case here, we see that our count is 0, and we end there, right? And as we've ended there, we have our divisor as so, and we have our value dividend as recorded as well. And then we got our accumulator as 1. So now, I want you to get your calculator and try to prove this. 7 divided by 3 goes in there 2 times, right? 3 divided by 7, 7 divided by 3 has got a value of 2 and has a remainder of 1. And we can see in our dividend value, we have positive 2 there, which is 0, 1, 0, which is positive 2 using 3 bits. And our remainder in the accumulator is 1. So you see, this is the restoring division algorithm for binary operations. If you are doing the restorative or restoring division, this is how you go about it. You follow this algorithm there, you shift left and subtract A from M. And then you follow these guys, and then once these operations are done, you decrement by 1 all the way until your value is 0. So again, if you do not understand this, try revisiting this question and going through step by step with me, trying to understand where you were left out. And if you still don't understand, please leave a comment and I will get to you as soon as possible. And also try different values and see if you get your answer. So if you want, you can try 5 divided by 2, and the value that you get in your dividend and your accumulator. So the accumulator is going to get the remainder, and then the dividend value here is going to get the actual value like so. So try 10 divided by 5. Any number, basically, you will see that if you do it correctly, you will have values. Or if you say 10 divided by 5, value here is going to be 0, and here we're going to have 2. So try that out, and if you don't get those values, please reach out to me and I will get to you as soon as possible. Okay, so now we have non-restoring division, right? And we're going to use the same example, 7 divided by 3. And this time we're going to have different setups for different non-restoring division, right? So again, we have our integer representation. This is just an integer representation. It doesn't really do anything. It's just to help you see what's happening in the accumulator. But our accumulator value is going to be there. We have our dividend and we have our divisor as so, and we have our account and our operation there. So without further ado, let's get into it. So now we say that if A, our most significant bit, is 0, right, meaning if it's positive, shift left the contents of the accumulator and the dividend, and then you perform the subtraction like so. So we shift left by 1 because this value is 0, right? So we shift left by 1, and when we shift left by 1, our value in the accumulator becomes 1, right? And then because it's positive there, we perform a subtraction. And we subtract from 3, basically like what we're doing with restoring division, and we subtract there. So once we've subtracted there, we get a value of negative 2. And negative 2 is there, as we can see, if it's negative. So now we're going to decrement the value by 1, right? And then repeat the process. So we have our value there, which is negative 2. But this time, notice that we are not doing any restoring or updating algorithm or restoring or updating feature. So we're just going to bring all the contents of everything at the bottom like so, and then we have our new initialization step. So this is step 2 now, and then we have our new contents in the accumulator. And we're going to say, is the value in the accumulator equal to our value that we're looking for? Is this value equal to what we're looking for, right? If not, then we shift left as well. If our value in the most significant bits here is 1, then you shift left the accumulator like so. So because this is negative, so we shift left the accumulator and the dividend, and then we perform an addition to that value. All right. So now we're going to add 5 to 3. Okay. So now when we add 5 to 3 there, we're going to get a value of 8. And when we get a value of 8 like that, 8 is positive like so. So if you didn't understand, or maybe if I've lost you, let me go back here to this point. So now we have subtract, right? So if we have this subtract here, we subtract 1 minus 3. 1 minus 3 is equal to negative 2, and the visual representation is that. So because this value is negative, we are going to shift left the accumulator, and then we're going to add a plus m, right? So because this is not restoring division, we are not restoring anything. We're just going to get every value here and then place it down like so, right? And then we have this guy here, we've decremented. So now, if the value is negative as well, right, we are going to perform a left shift. So when you shift left like so, we have a value of 101. So now, here we have a type of confusion here, or maybe you might be confused, but Trey, we have 101 here, and when you look at 2's complement, this means that this is negative 1. No, it's not, because 2's complement only applies to negative numbers. So here we have negative 2, right? So negative 2, we had to change it to 2's complement to be able to get this type of scenario, right? That's the way it is. 2's complement only works on negative numbers and not positive numbers. So meaning if this number is not being shifted, because we've shifted the value, so if the value has shifted, then this value becomes a number that is just a binary representation of sorts. So now, if you've understood that point here, this is going to be 5 in binary representation. And if we've shifted left, we add, because our value is negative, like so. So we shift left and then we add the contents of the accumulator. So we get the divisor and add it to the new value of the accumulator. So 5 plus 3 naturally is going to be 8, right? So if 5 plus 3 is 8, 8 is positive, right? Good. So if 8 is positive, it means that we go to our most significant bit, which is 0, and then the um, we shift left the accumulator and the divide or the dividend, and then we subtract. We perform a subtraction operation. Great. So now we also have these guys here, meaning if our most significant bit is 0, right? Meaning our last significant bit of q becomes 1, and if our most significant bit is 1 here, then our last significant bit of q is going to be 0. You get that correlation there. That's what happened here, and that's what's going to happen here. So now we've done all this, right? Our value was negative, and we've added there. And then after we've added, now we go to our most significant bit and say, okay, if our most significant bit is equal to 0, then our value that's going to be here is 1, like so. So now our new value is this, and then we decrement the operator or the count register by 1, and then we repeat the process. We shift left, and once we've shifted left, the new value in the accumulator becomes 1, and then we're looking for the value in this session. And when we find that value here, if the accumulator value is the most significant value in the accumulator is 0, then we perform the left shift like so, and then we subtract. So in this case, we are subtracting, right? So this is 1 minus 3, and then we see that this is the same as this, and when we do that, we get our negative 2. And if the value is negative, right, we say that the last significant bit of our dividend is going to be equal to 0, right? So we have that value by that. Okay, so now we have this scenario here. We have this scenario like so, right? So we have our value 0, 1, 0, that's 2, and we've gotten our answer, right? But then our value in the accumulator is negative 2, which is not right. So if the value here is not, if the most significant bit of A, when the count is 0, right, is not a 0 here, we are going to restore once the value A. So now we are going to restore. When we restore it to our shift value like so there, and then we just bring everything down like that. So now we see that our value becomes what we wanted. If not done correctly, you get different values and everything is going to be it's going to go haywire. So try to follow these steps properly, and if you do that, then you get your answer, or the answer that you're looking for. So our value here is going to be 0, 0, 1, and we have 0, 1, 0. Remember, every time you're restoring a value, you restore to the previous shift operation that was in the accumulator. You always restore the shift value that is previously iterated, not anything more than that, right? You don't restore anything else other than the shift value that was before. If it's updating, you just update this. That is for restoring division. But for non-restoring division, every time you see a restore there, you restore the previous shift value. And you see now here that our value is 2 and 1, of which 7 divided by 3 is 2, remember 1, like so. So that's basically the non-restoring division, right? We're not restoring anything except if we have a point whereby we have to restore, we only restore once. So that's basically it with the restoring and non-restoring division or binary division. And then finally we go to Booth's algorithm, which is binary multiplication. And Booth's algorithm basically goes something like this. So suppose you've been asked to find the value of 4 multiplied by 4, right? So in this session, I have the integer representation of what's happening in the accumulator and a new value here, or a new column that is going to help you understand when to stop, right? Good. These two operations here, or these two columns, are not part of the actual algorithm. I've implemented this to help you understand, much like I did with binary division, what's happening understanding this algorithm way easier and knowing or keeping track of what is actually happening if you have a problem with basic binary operations. It's easy to miss out some steps so you know where the value is actually wrong, right? So this is a Boolean operator. This column is going to tell us true or false, right? Good. So let's begin. So step one, we say identify whether, or we identify what the value is in integer form. With Boost algorithm, we are going to have specific steps. Identify what the value is in integer form, right? Good. So the value or the answer of 4 by 4 is 16. Identify what the value is in integer form, right? So we have 4 by 4, which is 16. So we know that our value is 16. We should get a value of 16, right? Step 2, translate all your values to binary, right? So if we have 4 by 4 is equal to 16, then 4 is equal to 0, 0, 1, 0, 0, and 4 is also 0, 1, 0, 0. And 16 is 1, 0, 0, 0, 0, right? Like so. And then using 4 bits, because we're using 4 bits, 4 is 4 bits and 4 is also 4 bits here. So meaning we get the majority here. And 4 bits of 16 is equal to 0, 0, 0, 0 value, right? Good. So now step 3 says understand 2 new rules. Rule 1 is said if the last significant bit of Q, right, here, if our last significant bit of Q and Q minus 1 column here is equal to 0 and 1, meaning if we have our value 1, if you have the last significant bit here and this guy here, then we perform an addition operation in the accumulator. And then after we perform the addition operation in the accumulator, if our value of A is equal to 16, our new value that we found there, then we end the operation. Otherwise, we shift right by 1. So notice that Boost algorithm is using shift right while division was using shift left. Okay, so don't mix these two up. So if the value here is false, right, you shift right by once. Else, if this value is true, then you end the entire operation. Okay, great. So now that's the operation if our value is 0, 1 there. So if here we have 0 and we have 1 there, like so, then you perform this type of algorithm there. If the last significant bit of Q and the Q minus 1 point is 1, 0, meaning if this is 1 and this is 2, meaning if here we have 1 and here we have 0, meaning our value, we're going to perform a subtraction operation, and we are going to say if A is equal to value, right, if this value is true, then we end. Otherwise, we shift right by 1, and then we repeat the entire process over and over again. So I hope you've understood this explanation. Write this down so that you'll be able to understand what we're doing, and let's get into actually solving this equation. Okay, so now we start here, right? Good. We start with a false value initially, right? Because this is when we're starting. So our initialization value begins with a false. So meaning we shift right by 1. So meaning we've shifted this value right by 1. See that this was 4 and then now this becomes 2, like so. But because our value here in our Q register, the last significant bit in our Q register and our Q minus 1 register is equal to 0, we write shift again because they're saying that we've shifted, so it's not basically giving us what we want. We say that this value is false and then we repeat the process by shifting right. So when we shift right here, we're going to get the value of 1 and 0. And notice that the 1 and 0 directly correlates to this scenario. So we subtract here, right? We perform the subtraction operation. So when we subtract, here we're going to have minus 4. So we subtract the M register here minus the A, right? So we subtract this. Here we have negative 4. And like I said earlier on in the division part here, if we have a negative, right, this value we have to turn it into 2's complement so that we perform addition. So when we turn this value into 2's complement, we are going to change this value into 1 there. And then now 2's complement value here is 1, 1, 0, 0. And if you do this basic operation of binary here or 2's complement, you find that negative 2 directly corresponds to 1, 1, 0, 0 in 2's complement, right? Great. So now that we've changed this into 2's complement, we can do our addition like so. And now we say that 0 plus negative 4 is still negative 4, right? Good. So now here our value is not equal to our value here in our accumulator is not equal to our 0, 0, 0, 0 value. So meaning we are going to shift right. And when we shift right, and because our value in the accumulator is not equal to our value there, we are going to say that's false. And then once we shift this guy, so this 0 goes all the way back there. It's kind of like a loop. So when this 0 moves all the way this side here, we have 0, 1, 1, 0. And in binary, this is 4 plus 2, which is positive 6, right? When we add a 0 like so. But then we notice that we have an addition operation when we shift the value because our 0 becomes there and we have our 1. So we have to add 4 to 6. And because our value in the accumulator is not equal to our value, we have that operation there. So we have 6 plus 4 because we're having an addition operation. And because we're having an addition operation, we can just add, say, 0 plus 0 is equal to 0, 1 plus 0 is equal to 1, 1 plus 1 is equal to 0, carry 1, and then 0 plus 0 is 0, plus 1 is equal to 1, right? Great. So now, when we have that value, we look at the value 10 here. 10 is not equal to our value there, so meaning we write shift and we declare this part as false, and then we write shift again. So when we write shift, we have 0, 1, 0, 1, and then we have 0, 0, 0, 0, and then we have 0 like so. And because this value is not equal to our value like so there, 0, 0, 0, 0, so this value is going to be false, and then we're going to shift right. So when we shift right by 1, we see that here this value becomes 2, right? This value in the accumulator becomes 2, and because this value is 0 and 0 again, we are going to shift right by 1 as well. So when we shift right by 1, we see that our value becomes 1 there, and then we have 0, 1, 0, 0. But this 1 here is not directly correlating to our value 0, 0, 0, 0, 0 there. So we say that's false, and then we shift there 0, 0, 0, 0, 0, and then we have 1, 0, 1, 0. And then in our last significant bit of q and q minus 1, we have 0 and 0, meaning we don't have any operations to operate there, so meaning we end at that point. So we perform the right shift, and once the right shift has been performed here, we see that our value is 0, which directly correlates to this guy, because this guy in 4 bits, 16 is 0. Basically, it's the same thing there. So we have 0, and then our value becomes true. So that's basically everything to do with the Booth's algorithm. Please review this in this entire binary multiplication step by step again if you do not understand anything, because it's very easy to slip up where values are concerned. So that's it with binary multiplication using Booth's algorithm. And if you need any help with binary multiplication, please feel free to reach out to me in the comment section, and I will get to you as soon as possible. Alright, so we are done with binary addition and subtraction, binary division, which is restoring and non-restoring algorithms, and then we have Booth algorithm, which is binary multiplication. We have finished all the arithmetic operations using binary, and that's it for this video. Thanks for watching, and if you found this video very informative, please do like and subscribe, and click the notification bell for future videos if you would like me to make more videos on this. Otherwise, thanks for watching, and I will see you in the future videos.